the assumptions made by Drude and Lorentz for electron theory, and on the basis of this we have to derive today the expression for thermal conductivity. As we know, the thermal conductivity is the property of a material to conduct heat. Means it is the ability of a material or conductor to allow the heat to flow through it. Okay, so that ability is called the thermal conductivity. And for this thermal conduct expression for thermal conductivity, let us consider the piece of metal having n number of free electrons per unit volume. Here we have considered one uh, cubical shape, or the somewhat parallelopiped shaped metal block. uh, this metal block is having suppose two opposite surfaces, here phase A and the second one is the phase B. Okay, and again we have considered the third phase at the center of the block. The block is having a length of capital L, and the area of cross section here is capital A. Here capital A is the area of cross section of this parallelopiped, and length of the parallelopiped is capital L, and this block having n number of free electrons per unit volume. Suppose if you want to calculate the total electrons in that block, then that will be the n number of electrons per unit volume into volume of that parallelopiped. That is, volume of parallelopiped will be A into L into N. That will be the total number of electrons in that parallelopiped. Okay, here we have maintained this block at two varying temperatures. Here the temperature of phase A will be TA. TA is the temperature of the phase A, and TB will be the temperature of phase B. Because we know for the conduction of heat, we require the temperature difference or temperature gradient is required. Okay. Similarly, for the case of current conduction, for the conduction of current, we require the potential difference, and by using external battery we will produce that potential difference. That means we made the one end at higher potential, that is positive potential, and other end at the negative potential. So due to the potential difference, the current is flows in the that block or that metal. Similarly, for the conduction of heat, we must have to maintain the temperature gradient, or the temperature difference is mandatorily meant to be kept between two surfaces. Okay, obviously here let us imagine the TA, that is temperature of the phase A, is more than the temperature of phase B. Okay, it is our assumption that the temperature of A is more than temperature of B, and as we know, the heat always flows from higher temperature to lower temperature. Okay, so this direction arrowhead indicates the direction of flow of heat. Okay, here this arrowhead indicate the direction of flow of heat, means heat flows from phase A towards the phase B. While flowing from A to B, it crosses the phase C. Okay, every time you should remember about the assumptions made by Drude and Lorentz. Okay, Drude and Lorentz made the assumptions. We have to use all these assumptions at each and every step. Okay, so let us see the further part. As we have considered the n number of free electrons per unit volume, means in an entire block, suppose n number of electrons are there per unit volume, then among these electrons, some electrons may be flows along x direction. Okay, some may be flows along x direction, some electrons may be flows along y direction, some electrons may be flows along z direction. because according to the Drude-Lorentz theory, electrons are treated as of free particles which are free to move within the entire volume of the metal. Okay, so in general case we may think that the some electrons or the equal number of electrons will be flows along one direction, and the same number of electrons will be flows along uh, the other direction and third direction also. Okay, so what will be the exact number of these free electrons? Let us see. So here we have considered the total number of n electrons are randomly flows in the that metal block. So among the n number of electrons, suppose n by 3, here we have three directions. So we may think that the n by 3 electrons are moving along x direction. Okay, n by 3 will be moves along y direction and n by 3 will be moves along the z direction. Okay, means equal number of electrons are flows along all x, y and z directions. Okay, in general case according to the assumptions of Drude-Lorentz free electron theory. So here we have along the x direction, suppose n by 3 number of electrons are moving. Among these, the half of the electrons moves along positive axis and half will be moves along the negative axis. So half of the n by 3 will be n by 3 into 1 by 2, that is n by 6, and upon 6 number of electrons are moving along positive axis in the sense positive x axis. Then n by 6 electrons will be moved along negative x direction. Okay, again n upon 6 electrons moves along positive y direction, and similar electrons will be moved along negative y direction, similarly for the z direction. Therefore in general I have mentioned here n by 6 electrons are moving along positive axis, that means positive x-axis, positive y-axis, positive z-axis, and n by 6 will be moved along negative x-axis, negative y-axis and negative z-axis. Sorry. So here negative is mentioned because suppose at this point, sorry, suppose we have the origin. Okay, then along this direction, suppose n by 6 will be moved along this direction, n by 6 will be moved again along this direction, n by 6 moves along this direction, n by 6 moves, similarly for the z axis. Okay, so in general case we may think that the n by 6 electrons moves from positive direction or moves towards positive direction, and by 6 moves towards all negative directions. Okay, so let us see the further part. Now as we know the uh, n by 6 are moves along each of positive axis and each of negative axis. Let us see the v be the average thermal velocity of electrons at temperature T, because according to the kinetic theory of gases, the at any temperature T, the kinetic energy possessed by gas molecules or here electrons will be 3 by 2 kT. Okay, and at temperature T, its general speed or average speed will be v. Some electrons may be moved with velocity v1, some with v2, v3, v4 and so on. Okay, and the average of all these velocities will be v. So here v is the average thermal velocity of each electron at temperature T. And we know when the electron moves with the velocity v, then its kinetic energy will be half mv square, provided m is the mass of that electrons. Okay, here half mv square will be the kinetic energy purchased by each electron having average thermal speed as a half mv square. Okay, now let us consider three planes of the metal as A, B and C, such that Ta is more than Tb, which is I have already mentioned to you that Ta, that is temperature of the first phase or the phase A, is more than the temperature of phase B. Okay, therefore heat is flows along the direction of this arrow. Okay, now let us calculate the average kinetic energy of electrons crossing the plane C from left hand side. Here suppose we have the at plane C we have the origin. Suppose at this position we have the origin O. So at origin the n by 6 number of electrons are moving from left hand side towards the O. Again, the n by 6 number of electrons are moving from right hand side at plane C. Okay, because it is our positive axis, it is the direction of negative axis. Suppose if we consider the origin at the center of the block, so we have n by 6 number of electrons crossing the plane C or the central plane C from left hand side. Okay, that means from phase A towards the phase C. Are you getting? N by 6 number of electrons are moving from phase A towards the phase C. So we know the average kinetic energy of single electron will be 3 by 2 kT, or sometimes K is in place of K we can mention here KB as a Boltzmann's constant. Here K is a small. Okay, in this case on the in this expression for thermal conductivity we use the coefficient of thermal conductivity as a capital K. So to distinguish the capital K and small k, we have here put the suffix B as a Boltzmann constant. We know the thermal kinetic energy of single electron will be 3 by 2 K Ta. Ta refers to the temperature of phase A, because here we are considering the electrons moving from left hand side. Therefore, the kinetic energy of electrons at the phase A is to be considered. Okay, into total number of electrons crossing. So the total or the average kinetic energy of electrons crossing the plane C from left hand side will be energy of single electron, that is 3 by 2 kb into Ta into total number of electrons crossing, that is n by 6. Okay, into V, because we have calculated here the kinetic energy, so into V should be there. Okay, n by 6 into V gives you the total number of electrons. Here 3 and 6 is there, so 3 and 3 get cancel, so in the denominator 2 into 2, that is 4 is there, and the numerator side n we have put in the front and kb into Ta. So n v kb Ta upon 4 is the average kinetic energy due to the electrons crossing from left hand side towards the or to the plane C. Okay. Similarly, the average kinetic energy of electrons crossing plane C from right hand side. So from right hand side, the same number of electrons were coming, okay, that crossing the plane C. Therefore, the total kinetic energy will be also same. Only difference is that here electrons are coming from phase B. Therefore, we need to mention here temperature Tb. Here 3 by 2 kb into Tb is the kinetic energy, thermal kinetic energy of single electron into total number of electrons crossing, that is n by 6 into V. So it will be NV kb into Tb by 4. So we know the NV kb into Ta upon 4 is the average kinetic energy due to electrons from left hand side, and NV kb into Tb upon 4 is the average kinetic energy due to electrons coming from right hand side. So the net kinetic energy will be, hence the extra amount of thermal energy or net kinetic energy, the net thermal kinetic energy at C will be 3 by 2 kb into Ta minus 3 by 2 kb Tb into n by 6 into V. Okay, I have taken the n by 6 into V as a common and substituted 3 by 2 kb Ta minus 3 by 2 kb Tb. Here 3 by 2, here 3 by 2 is taken common outside the bracket, and 3 on numerator and 3 on denominator got cancelled. So these 3 and here 3 cancel. So here only 2 remains. 2 2 into 2. So it will be 4. Okay. 1 by 2 taken common, 1 by 2 into 1 by 2. So that will be 1 by 4. So the equation will be NV upon 4 into Ta minus Tb. Okay, Ta minus Tb, that is our equation 1. So equation 1 gives you the resultant amount of thermal energy at C due to electrons coming from all directions. We may say that electrons coming from all directions. Now it is about the half part of the expression. So in the half part we have calculated from the geometry of the figure. Okay, from the geometry of figure. Now from the theoretical or interpretation, we have or we can define the thermal conductivity as the amount of heat or thermal energy transferred per second from temperature Ta to the Tb. Okay, the thermal energy or the thermal conductivity means amount of thermal energy transferred in 1 second from higher temperature to lower temperature, that is denoted by capital Q. Capital Q here is the amount of thermal energy, and this amount of thermal energy transferred from one temperature to the lower next temperature per second is always proportional to area of cross section of the that conductor. Okay, area of cross section of the conductor, it is inversely proportional to length of the conductor. Here D is mentioned, D or L, we can write anything. In this case, into, or it is always again proportional to temperature difference between two ends, that is Ta minus Tb. Sometimes here dt can be written as, okay, so Q is directly proportional to A into Ta minus Tb and inversely proportional to D. And if we remove the sign of proportionality, put the constant K, and that constant K is called the coefficient of thermal conductivity. So coefficient of thermal conductivity is the thermal energy transferred in a unit length of conductor per unit area of cross section per degree rise in temperature. Okay, this definition is prepared by changing this equation. Means if we send this D in the numerator side, A on the denominator side, and this Ta by Tb in the denominator side, so we can easily define the coefficient of thermal conductivity. Here equation 2 is the amount of heat transferred by using the theoretical calculations. Okay, in this equation 2, suppose we have the particular conductor having area of cross section as a unit, and if the length of conductor equals to 2 times mean free path length, then we can simply change this equation to this form. Means if A is put equals to 1 meter square and D equals to twice lambda, means if the length of conductor or metal block is taken as a 2 times mean free path length. Mean free path, you know about the mean free path length. Mean free path length is the distance traveled, average distance traveled by electrons during successive collisions. Okay, means whenever electrons collides with the walls of conductor or to the other electrons, during their collision it travels along a straight line direction in a Brownian motion, and that average distance traveled between two successive collisions is called mean free path length. Okay, so here lambda is the mean free path length, and if we take the length of conductor equals to 2 times mean free path length, So the equation can be changes to the form Q equals to K into 1 upon 2 lambda Ta minus Tb. That is our equation number 3. Okay. Now equation 1 is calculated from the geometry of the figure. Equation 2 3 is calculated from the theoretical assumptions of the thermal energy. So from equations 1 and through 1 and 3, here we have equation 1 I have put here, and VKB upon 4 into Ta by Ta minus Tb. Equation 3 is here, and both these equations gives the same quantity, that is the heat transferred from one end of the conductor to the other end of conductor having temperature difference of Ta minus Tb, and area of cross section as a, length of conductor as a d. Okay, so we can equate equations 1 and 3. Here equation 1 is put on left hand side, equation 3 is on right hand side. Now we can cancel the 2 on both the denominators. Ta minus Tb also cancels. Okay, so equation changes to the form NV Kb upon 2 equals to capital K upon lambda. Here K is the coefficient of thermal conductivity, and we are interested in deriving the expression for this. Okay, now this send this lambda to the numerator of LHS. So the equation changes to the form K equals to NV Kb into lambda upon 2. That is equation number 4. And equation 4 is the required expression for coefficient of thermal conductivity. Okay. Here we can say that the coefficient of thermal conductivity, or the ability of conductor to allow or permit the uh, heat through it per second, is depends upon n, that is number of electrons per unit volume contained in a conductor. If for particular case the number of electrons are more, then its ability to transfer or to allow the heat also more. Again, it depends upon average thermal speed, okay, or mean velocity of the each electrons, depends upon Boltzmann constant and mean free path length. If the mean free path length is more, it have the more ability to transfer the heat. Okay, because during a mean free path, it the electron travels with very high velocity. Therefore, if the collisions are less, okay, collisions are less means the mean free path length will be more, then the thermal conductivity will be again more. So it is about the today's expression. Thank you very much. Now you can ask me any difficulties about the topic if you have.